All right, so for today's video lesson, we're going to be talking about thermal energy transfer in the hydrosphere. Okay, so remember the hydrosphere is one of the three components of the biosphere. So we have the lithosphere, so that is the land, that's what we're all standing on right now. We have the atmosphere. So remember we had like the lithosphere, or sorry, not the lithosphere, but we had like the stratosphere, the mesosphere, right? We had different components to the atmosphere. And lastly, we have the hydrosphere. So those three components will make up the biosphere. And remember, the biosphere is pretty much all the areas on Earth where humans are able to live and also other organisms. Okay, so today we're going to talk about the hydrosphere. So the hydrosphere is related to water. Okay, hydro, water. Okay. So let's go ahead. Okay. So we know, and we've discussed this a few times already throughout this year, that water is able to hold a lot of energy when it's heated. Okay. And if you don't believe me, don't actually do this, but you know, if you were to put your hand into a pot of hot water, right, that would be really uncomfortable. You'd probably get burned. The water holds a lot of energy when it's heated. Because of this property,
You guys, I'm on my Zoom meeting.
Because of this property of water, regions that are closer to large bodies of water are going to experience less dramatic temperature changes throughout the year. So we've talked about Vancouver a few times. So remember, this image in the bottom right corner of your screen is called a climatograph. So it's going to compare the precipitation that a region receives and also the temperature. So note for Vancouver that even in the summer, June and July, it only gets up to about 18, 20 degrees Celsius. But in the winter, in January and December, it hovers around 2 to 3 degrees Celsius. Okay, this is because it is right beside the Pacific Ocean, and the Pacific Ocean, and all of the oceans for that matter, do store quite a large amount of heat. So in the cold months, the ocean will kind of release some of this heat, and this is going to reduce those dramatic temperature changes that we've been talking about. I have a climate graph up at the top right corner of your screen for Lethbridge. And because Lethbridge or Vauxhall were much further away from the ocean than Vancouver, of course, we are going to experience much more dramatic temperature changes throughout the year. And this is because we don't have the big body of water to regulate those changes or to buffer it, right? So if we look at January and December for Lethbridge, usually we have a high of about, around 0, -4, but it can get to a low at nighttime around -15. Okay, those are in the winter months. In the summer months, we can get pretty warm days sometime. I remember a couple summers ago, we broke the daily heat record, and it was like 43 degrees in Lethbridge. That was awesome. Yeah, so because we are further away from the ocean, we just don't have that. We don't have the ocean to kind of regulate our temperatures here. So just kind of paraphrasing what I said, regions that have small amounts of water tend to heat and cool faster than regions at similar latitudes near water. Okay, so today's two topics, we're going to be talking about specific heat capacity. So specific heat capacity is going to be unique to each substance, okay? So the heat capacity of water is going to be different than the heat capacity of aluminum, and that will be different than the heat capacity of olive oil or iron, etc. Okay, so these specific heat capacities are unique to each substance. Okay, so this measure here is the amount of energy required to raise the temperature of 1 gram of a substance. It doesn't just have to be water by 1 degree Celsius. Okay, so make sure we know this point right here. Okay. The specific heat capacity of water is 4.19 joules per gram degree Celsius. So to increase the temperature of 1 gram of water by 1 degree Celsius, we need 4.19 joules of energy to do that. Okay, and underneath the specific heat capacity of water is the specific heat capacity of aluminum. Okay, again, the big takeaway here is that substances will have different heating capacities. So this is the formula we're going to use to calculate the thermal energy change of the system. You will be given this formula for tests, so don't worry about remembering that. Okay, you will need to know how to do these questions. They will be on the final. Okay, so make sure we're paying attention and we're able to complete today's topic. Okay, so Q is equal to MC delta T is our formula. Q is going to be the quantity of thermal energy in joules. M is going to be the mass of the substance in grams. C will be the specific heat capacity of the substance. This will be in joules per gram degree Celsius. And delta T is going to be the change in temperature. Okay, remember delta T can be found by finding the second temperature, subtracting the first temperature. Okay, sometimes we will be given the change in temperature. Sometimes we're going to need to find it. Okay, so here's the formula. Here are what your variables mean. All right, so let's try to solve one. Oh, before that, we have a thought question. So metals are generally good conductors of thermal energy. So think of our cookware at home. Would the specific heat capacity of metals be higher or lower than the specific heat capacity of insulators? So remember, the insulator is going to want to kind of keep things warm, okay, like a coat. That's why we wear coats. It's like an insulator. So generally we would have a discussion in class. Because you guys are not here, I'll just answer it. We would expect to find the specific heat capacity. So C, remember that is the specific heat capacity. C will be higher in insulators. And this is because we want those insulators to be able to absorb a lot of heat before emitting that heat. Okay, so for a frying pan, it would have a lower specific heat capacity than an insulator would. Okay, and again, we want if we're cooking, we want our metals to be able to conduct heat easily. So we want them to have a low specific heat capacity. We don't want it to be a high value, because the higher the value is, the more energy we're going to have to put into the system to be able to change the temperature of that system. Okay, now let's get into solving a calculation. Okay, so the question reads, how much thermal energy is required to raise the temperature of 3 grams of gold by 6.5 degrees Celsius? And in this question, we're given the specific heat capacity of gold. It is 0.126 joules per grams degree Celsius, okay? So when we are trying to find the thermal energy, that is going to be our Q. Okay. So in this case, we don't need to do any isolating, we just need to solve this problem, okay? So like we've been doing throughout the semester, let's write down our knowns. So we know that the mass of the sample is 3 grams. We know the specific heat capacity of gold. Okay, and we also know the change in temperature here is 6.5 degrees Celsius.
How do you measure a joule per gram Celsius?
Good question. So we have this thing, it's called a calorimeter. Have you guys heard of that before?
Sounds complicated.
It's actually really not that complicated. I'll draw a crude picture. So is what it is. It's literally like at the most basic calorimeter is literally a styrofoam cup. Okay. And you will have a solution of water in there. And is what is going to happen. So when you're trying to find the specific heat capacity, you would put like a chunk of gold in here, say. You would have a thermometer sticking out of the side. And is what you do, you would measure the temperature of the system before you put the hunk of gold in. And then then you would put the piece of gold in, you would weigh the gold, right? And then you would measure the temperature change in the calorimeter. Okay, and then you can derive from that the amount of energy or the specific heat capacity of a substance. Did that answer your question, Justin?
Yeah.
Cool. Okay, good question, really good question. Okay, so now that we have all of our variables and Q is isolated because we didn't have to do anything, we can just substitute in. So Q is equal to MC delta T. So M is 3 grams, C is 0.126 joules per gram degrees Celsius, and then multiplied by that change in temperature, which is 6.5 degrees Celsius. That is 6.5. Okay, punch this into your calculator, and you should get a value rounded to sig digs. So we have 2 here, 2 here, and 3 here. So our answer should have 2 significant digits, and we should get 2.5 joules. Pretty straightforward. Any questions there? Perfect. Okay, so this next question here, we are looking for the change in temperature. Okay, so calculate the change in temperature that will occur if 1.25 kilojoules of thermal energy is added to 150 grams of olive oil. We know the specific heat capacity of olive oil is 2.10 joules per gram degrees Celsius. So let's write down our variables. So we're looking for the change in temperature. We're adding 1.25 kilojoules of energy, so that's going to be our Q. Our mass is 150 grams, and C, our specific heat capacity is 2.10 joules per gram degree Celsius. Now, hopefully you notice that Q is in kilojoules and C is just in joules. So we have to be careful there. So let's change our kilojoules to joules. So we'll multiply this by 1,000 joules per 1 kilojoule. Okay, so kilo is the prefix. It's just like saying there are 1,000 grams in 1 kilogram. We're just dealing with joules here. Okay, so 1.25 kilojoules is equal to 1,250 joules. Now that our units are now that we have the same units, we can isolate for the change in temperature. Okay, so change in temperature is is being multiplied by mass and the specific heat capacity. So the opposite of multiplying is dividing. So I'll divide both sides by MC. Those will cancel, and we will be left with change in temperature is equal to Q over mass times the specific heat capacity. Okay, so at this point we can just substitute in our variables. So change in temperature is equal to 1,250 joules divided by 150 grams multiplied by 2.10 joules per gram degree Celsius. Okay, if we punch those into our calculator and round it for sig digs, we will get a change in temperature of 3.97 degrees Celsius. Okay, and in terms of units, because we're multiplying a gram per joules grams degree Celsius, these will cancel. We're dividing a joule by joule, so those will cancel, and then we will just be left with degrees Celsius for temperature, which is awesome, because that's what we should expect. Okay. All right, one more example with our Q formula. So we are calculating the thermal energy released when 60 grams of glass cools from 87 degrees Celsius to 22.5 degrees Celsius. Okay, so remember our change in temperature, our delta T, is equal to T2 minus T1. In this case, our T2 is going to be the 22.5 degrees Celsius, and our T1 will be 87 degrees Celsius. So delta T is equal to 22.5 degrees Celsius, subtract 87 degrees Celsius. So 22.5 subtract 87 will give us a change of temperature of negative 64.5 degrees Celsius. So now that we know delta T, we also know that our mass is 60 grams. And our specific heat capacity is 0.840 joules per gram degree Celsius. We are looking for the thermal energy released, so we're looking for Q. So we can just go ahead and substitute in our values now. So mass is equal to 60 grams. Specific heat capacity, 0.840 joules per gram degree Celsius, multiplied by the change in temperature, which is negative 64.5 degrees Celsius. Okay, we punch these into our calculator. We will get a value of negative 3,250.8 joules. And hopefully you're saying, Mr. Jones, that is too many significant digits. You're absolutely right. We have 3 all across the question, so I will present mine with 3. So you could either write this here in scientific notation, so 1, 2, 3. Or you could convert the 3,250.8 joules into kilojoules. So if you divide that by 1,000, you will get negative 3.25 kilojoules. All right. Are there any questions with those types of calculations? Cool. So for the 3 questions that we just did, this is finding the energy released when something cools from, or when something warms up from 2 particular temperatures. The next couple problems we're going to talk about are when these substances are changing phases. Okay, so note that these ones, when we're calculating thermal energy, there are no phase changes here. Okay, but the next problems when they're changing phases, we're going to have to use a different formula, but it's not tricky, so don't worry about that. So just know that when we're calculating thermal energy, this is when there are no phase changes, just a change in energy. Okay, so freezing, melting, evaporating, or condensing, these are all called phase changes. So right now, today, I think a lot of the snow that's on the ground is going to melt, right? So snow is water in the solid state, right? So that's going to melt into liquid water, which will eventually go into the ground. The amount of energy required to melt 1 mole of a substance is called the heat of fusion. So melt, so going from solid to liquid. Okay, it is fusing into a liquid. And then when we have a substance going from a liquid to a gas, this is called vaporization. So we will use HVAPs, is what we'll shorten that for, when we have water going from like liquid water to steam. Okay, and when we're going, so liquid to steam for water, for example, or ice to liquid. So just note that when we are going from solid to a liquid, or when ice, when ice is melting to liquid water, we will use H fusion for that. And when we are going from a liquid to a gas, we call that heat of vaporization. Okay. So these are going to be different. So heat of fusion and heat of vaporization are going to be different. Here are some values for some common substances, okay? One thing you need to note here is that these units are in kilojoules per mole. Okay, so just be careful with our units here. We just got to make sure that we are using joules with joules or kilojoules with kilojoules. Okay, so you guys are not expected to memorize this table, but I just wanted to show, just to kind of compare the differences between the heats of fusion and the heats of vaporization.
Is there a reason it's like heat of fusion? Why isn't it just heat fusion?
That's just what they call it.
Oh, okay.
Good question. Okay, and you guys will be given like the heat of fusion and the heat of vaporization on a test, or maybe in some questions you're going to actually calculate the heat of fusion, but it's not too tricky. Okay, so here's our formula for heat of fusion. So this is the energy required for melting. So Q is equal to N times the heat of fusion. So Q is going to be the amount of heat again. The number, so N is going to be the amount of moles. And heat of fusion is going to be the heat of fusion for the substance, okay? So just be careful with these. So just be careful with joules or kilojoules, okay? Just make sure we are taking note of what units were given, okay? That's really important for this. But other than that, it's pretty straightforward, okay? So that was for melting. So this is conversely the heat of vaporization. So this is the energy required to convert a substance from a liquid to a gas. So it's pretty much the identical formula. We just have H-vape or H-vape, whatever, instead of H-fuse. So Q is equal to N times H-vape. Okay. Again, you will be given this formula for the final, so don't worry about memorizing it, but you do need to know how to use it. So Q is equal to the amount of heat, N is the number of moles, and HVAP is the heat of vaporization for that substance. And again, just be careful here with joules and kilojoules, okay? Because that's one area where we could get in trouble here. Okay, so we have 2 questions and then we will be done for the day. So we have a liquid beaker which contains exactly 360.4 grams of water in the liquid state. And this is at 100 degrees Celsius. How much energy is required to convert the liquid water to water vapor at 100 degrees Celsius? Okay, so notice that there is not a change in temperature here. So that could be a good indicator that we should not use our Q is equal to MC delta T formula. Okay, and it mentions that there is a phase change. So it's as soon as you see phase change, you need to think of Q is equal to N times H vaporization or H fusion. Okay, in this case, we're going from a liquid to a gas, so we will use the H vaporization here. Okay, so we are given a mass of water in grams. Now remember, N needs to be in moles here. So this is going to be a little bit of a chem refresher, which is great because you guys are going to need to know this for the final. So remember, number of moles is equal to the amount of mass. That was a crazy M. Is equal to the amount of mass, so little m over big M, where big M is the molar mass. Okay, so here our mass, our little m is 360.4 grams. And the molar mass of water, so remember water is H2O. It has 2 hydrogens and 1 oxygen. So hydrogen has a molar mass of 1.01 grams. Times 2 because there's 2 of them, 2.02 grams for the hydrogen plus 16 grams for the oxygen, giving us a molar mass of 18.02 grams per mole. Okay, so that's going to be our big M. And if we punch that into the calculator, we will find the amount of moles that we have present. So 360.4 divided by 18.02 is equal to 20. So we know we have 20 moles of water here. Okay, so now that we have our N and we have our H vaporization, which we're given, we can just go ahead and solve for Q. So Q is equal to N, so 20 moles, multiplied by our heat of vaporization of water, which is 40.65 kilojoules per mole. Okay, kilojoules, so just be careful there. And as we multiply those, the moles will cancel, and we will just be left with kilojoules. And our answer rounded to 3 sig digs, we have 3 right here, would be 813 kilojoules. Okay, so not too bad. We just need to remember how to calculate moles from a mass. So this is good review for our chemistry. Okay, last question of the day. So we have a container holding 243 grams of ice at 0 degrees Celsius, melts to form liquid water at 0 degrees Celsius as well. So how much energy must be added for this to occur? So we have a phase change here, so we should use our Q is equal to N times heat of fusion formula. We're given a mass of water. So again, we need to find the amount of moles that we have present. So N, number of moles, is equal to the mass of the sample, so little m, over the molar mass, which is big M. Okay, so in this case, the mass of our sample is 243 grams. And the molar mass of water, we just calculated the last slide, H2O, is 18.02 grams per mole. So if we punch that into our calculator, we should get a value of 13.48501.665 mole. Now, if you're asking yourself, Mr. Jones, why are you adding so many decimals to our moles? Well, remember, in this particular case, N, the amount of moles, is just going to be an intermediate, right? It's not our final answer. So we do not want to round our intermediate calculation numbers. Okay, so now that we have moles and we know our heat of fusion of water, we can just substitute this into our formula. So Q is equal to the number of moles, so 13.48501.665 moles, multiplied by the heat of fusion of water, which is 6.01 kilojoules per mole. So just be aware. Okay, the moles will cancel. And if you multiply these two numbers together, and if we round it to 3 significant digits, we'll get 81.0 kilojoules. Okay, so that is it for today's topic. So I hope that was helpful. And if you have any questions, just let me know and I'd be happy to help you.